Hello everyone, and thanks for coming to our talk on Cards Against AI, predicting humor in a fill-in-the-blank party game. The work is about predicting humor in Cards Against Humanity, done together with Daphne Shachaf at the Hebrew University. So, we aim to understand humor. We believe it is important for improving human-computer interactions and for many other tasks, for example, finding interesting content or just understanding human behavior and motivation. And we view this through using data. Now, the overall problem is one of humor recognition, whether something is funny or not for a given context. And the popular board game Cards Against Humanity, or CAH, gives a unique perspective on this problem. So, we managed to acquire a large data set of Cards Against Humanity games. The way the game works and how it's played is as follows. A player is presented with a black prompt card and 10 potential white punchlines. And they need to pick which punchline makes for the funniest joke in combination with the prompt. So in this scenario before us, I might say white people like knock-knock jokes as being the funniest joke. So the dataset is unique in a number of ways. For one, this is a ranking problem. It's not picking whether something is a joke or not. It's picking what's the funniest joke. For example, and also the fact that it's a novel dataset which has not been used before, especially with these labels. Also that the player behavior is quite different. It's people who play the game online for free as opposed to college students in a psychology department answering what they think is jocular or not next to their professor. Also the fact that we have very clear negative labels, which cards were picked as not being funny compared to the others. In short, it's large, labeled, and diverse, and though with horrible humor. I will note some of the jokes are very inappropriate. So we had about 300,000 games, millions of jokes, hundreds of prompts, thousands of punchlines, a huge number of combinations, a gargantuan amount of combinations for a possible game. Player level information was excluded in advance due to privacy promises. So the setup is, given a prompt and a potential punchline, what rank can select the funniest punchline, which will yield the best joke in combination with the prompt, or in other words, to rank and to classify the best one, and to find the best joke. We see that the win rate of different punchline varies greatly, with some being far more or less successful. Or in other words, that some of them are far more likely to win regardless of their context. We see some examples for successful punchlines. What you can see here, basically these are highly censored, I will know. These are not actually the top most successful ones, but in general, all tend to be very short, dirty, and explicit, and outperform the average by about twofold. Unsuccessful punchlines were a bit harder to characterize beyond being relatively long, and I would say having a few more brain cells involved. I will note that the unsuccessful ones were far less successful relatively than the successful ones were better. They are 5 times worse. We also looked at jokes which were uniquely outperforming, i.e. a combination of a prompt and punchline that tended to win far more on average than that which would be expected just by the punchline itself. I.e. if a punchline wins 20% of the time and the joke wins 30% of the time and it appears enough times, I would consider that to be outperforming. I will note that these are actually definitely the best jokes to my mind. They were tended to be quite amusing and very good combinations. Again, these examples are highly censored. We used an automated machine learning framework to help extract many features from the different inputs, the punchline, the joke, the prompt, and so on, and various sources, word embeddings, WordNet, interactions between the columns, knowledge graphs, and so on. And this shaped our subsequent analysis of the data, given what we found was that the punchline was the most important part. So some features towards winning jokes were very much strongly focused on the punchline. And also they tended to be around very dirty, gross out, puerile jokes of the punchline, obscenities, and so on. Also very short terms and words. Low win rates were harder to characterize, beyond maybe the fact that some about being positive emotional stuff. So we then started training machine learning models to predict the winning joke out of each round. So again, 10 cards per round, so top accuracy at top 1, randomly guessing will get you 10%. We made multiple baseline models for the popularity of the joke, as well as the popularity of the punchline regardless of the attached joke. The punchline greatly outperforms the joke and is a very high level of performance. We trained multiple machine learning models using the features from the AutoML, as well as comparing them to, say, deep learning models using pre-trained models, Albert and Roberta, which greatly underperformed, and sentence transformers. the mini-EMNLP model. We also use these embeddings as input features for the final cat-boost classifier model and the cat-boost meta model. The cat-boost meta utilized all the above features, text features, embeddings, as well as additional features such as the number of words in the text, as well as card order. This was the only model which managed to outperform the punchline popularity baseline. The other models at best matched it. We also did some ablation testing to support this. A model trained purely using the punchline outperforms one using the more combination from the data, i.e. the rest of the stuff is just noise for the model. In short, the best models are twice as good as random, so they definitely learn stuff even without having any information on the specific user. Deep learning, inferior. The punchline popularity is a very strong baseline here. And our conclusion was that the majority of the signal really is in the punchline's fire win rate and not their semantic combination, which is what we expected, given that's how I play the game. I'll also note, by the way, that this model and the base, as well as the baseline, handily outperforms humans that we tested on with a subset of the data. So the question arose, were the models actually learning anything about humor, or were they just memorizing the popular punchlines? So we set up a new task of predicting the winning jokes, which was split up at the level of the punchline instead of per game, and repeated this many times till we had a very large evaluation. So in this scenario, the popularity baseline could not do any better than random, since no punchline would repeat itself between the train and the test set. However, the models did generalize. Performance was lower, but it still got about 15% accuracy as opposed to 10% for random. So it did learn something about the humor even without user information or the like. So in all, the dataset is a novel and challenging one, both for the ranking problem and both other aspects about it. Additionally, the fact that, again, ranking is just much harder than whether something is funny or not, especially given the fine-grained differences between jokes. It's talking about very small differences. The punchline and popularity baseline is extremely strong in this dataset, outperforming deep learning models handily. And deep learning in general greatly underperforms here, even with pre-trained models and the like, and some augmentations. Additionally, we'll note, of course, that this is only for a subset of people who know about the game and have access to the internet. It's not a representation of all players. Even myself, I play it quite differently. And there's definitely a lot of room to improve on this task and more stuff to analyze, especially if there was a way to access user data. But in general, it's like definitely a new arena in terms of humor. So I hope you enjoyed the talk, and come talk to me at the poster about the paper, and thank you very much. I'm Dan Alpha.